Welcome to Krishna's classroom. We begin with another episode of the lecture. I am Krishna Kumar. The second part of the series of lectures on Riemann integration looks at the following problem. How do we connect the antiderivative with the geometric notion of integration? Because you recall last time we said if f is a given function on some interval. Now the question that you are asking is, does there exist a function capital F such that f derivative is equal to f? This is the inverse problem that we are looking at. And if such a solution to this problem exists, then you call it f is called the antiderivative of f. Now that is one notion about integral, and you called it the integral of f. Now how do you connect this with the geometric notion of integration? Now you know that given a function, you can draw the graph of the function and then you associate normally the area enclosed between the curve and the x-axis and the ordinates at a and b as the integral of, write it normally as integral of a to b ft. So the central problem is this: how f and this integral are connected. Okay? How do we normally look at such problems? First, consider a number of examples and get a feeling for what to expect. And then you make it a theory or prove some theorems to connect them up or disconnect. I mean, depends on whether your conjecture is right or wrong. As I was telling on several occasions, that in the natural sciences, it is the observations and the experimental data that serves to give a guidance for building up a theory. In mathematics, it is solely credible examples. Therefore, let us start with some examples and try to examine this problem. We take the first example. Define equal to the constant c for x belonging to the interval. We assume, without loss of generality, assume c is positive. Let us draw the graph of this function. How does it look like? Now, let me compute the area of the area enclosed between the curve, the ordinates at 0 and 1, and the x-axis. Or more generally, you choose an x on the interval 0, 1, compute the area of the rectangle 0x cross 0. For each x, this will give you a particular number which depends on x, obviously. Therefore, it defines a function. Let me call this the area function. So let me define ax to be equal to the area of 0x cross for every x 0. So that defines a new function on the interval 0. What is it? How do you compute it? One side is a rectangle, one side is given by x units, the other side is given by c units, and ax is equal to cx. Now, one observation that you made is that you can recover f from the function a. What do? If you differentiate this, you are using differential calculus. If you differentiate this, then you get a derivative of x equal to c, which is essentially f of. Therefore, if you look at this equation, f derivative equal to f, that is the inverse problem associated with the f for finding the antiderivative, then you see that Ax is a solution of the equation f derivative, capital F derivative equal to f, or capital F is given by Ax. So in this case, capital F is equal to A. Okay, so the area function essentially gives you what is called the antiderivative of f. Ax is an antiderivative of f. So we have successfully computed the antiderivative, and this antiderivative has been connected with the area. It looks very promising. Once you are able to compute the area function, then you get the antiderivative of the given function. So that's a very well defined way of computing this. You also observe the following. A0 equals 0. Now look at it more general. On the interval 0, 1, the same problem. C, but we choose 2 points A and X such that now compute the area of the rectangle. So area of the rectangle designated by, give a notation, that is, it depends on A and X, is computed to be what? It is actually C into X minus A, or now C and A are constants, therefore this is a constant and this is X. Once again you observe that this is also a derivative is equal to C. So this is also a solution of your problem, or this is also an antiderivative, and the difference between the area function that we have defined earlier and the area function that you have defined now is that they differ by a constant. So you see that this is actually, this is equal to this, and a derivative of. So the two area functions differ by a constant. So you see that the statement I made that there are several antiderivatives that you can have for a given function. In fact, the reason is that if you have a constant function and differentiate it, you get a 0. Therefore, if capital F is the antiderivative of small f, then you know that capital F plus C is also antiderivative of, that is what is reflected here. Anyway, let us write this down, but I am interested in this sort of information. So let us take a slightly more sophisticated example. Still, it is very elementary, I should say, but let us see. Working on elementary examples do give a lot of experience, lot of insight. So you go in stages, in steps to complexity, not directly jump into a very general problem and then work on it. Let us see. We consider another function. Without loss of generality, we assume m is greater than 0. Let us draw the graph of this function. We did exactly do whatever we did in the previous case. 1, 0, 1. So you know that y equal to mx is something like this. Okay, so this height will be equal to. Now this is the graph of the function. Once again, let us compute the area function. So the area function in this case is that you choose x that lies between 0 and 1, you can easily see that AX is equal to, now it is a triangle whose area you have to work with, and it is a triangle joining the points 0, 0, x 0, and possibly x mx. Okay, so that's the triangle. So right angle triangle is quite easy to find the area of that. This is equal to half of x into the altitude is m. Well, this is equal to half of x. Once again, you immediately verify that a derivative of x, because you are encouraged by this observation, this is equal to x. And that is a function that we started with, and this is equal to f of x. And this is true for every x belonging to interval 0. Therefore, the antiderivative of fx equal to mx is given by the area function again. So the area function gives an antiderivative of what did we do? What more we did? Recall that what more we did? We actually picked up a point A here, A and x lying on the interval 0 to 1, and then worked out the area of the sort of trapezium that you have here. This is the trapezium that you have here. We computed the area of the trapezium and call that A, same notation we use, and this is equal to, now you see there are two things here. One of course x minus a into ma, same ma, because this height is ma, and then this triangle, so plus half of, and one observes that this is again equal to ax minus a. You observe that a of the interval ax associated with the interval ax is also an antiderivative of the given function, because if you differentiate this, you get again x, principal delta of x. So you see that there are several antiderivatives that you can have, because the difference between any two antiderivatives is a constant. Ax equal to half of m x squared. So let us draw that. So at 0 it is 0, and at 1 it is gives half. So this is m, then by 2 is this. You see that it's parabola. It's a portion of the parabola passes through these 2 points. If you work out the slope of that, you will get x. Now we take the third example. So this is the graph of the function. And you see that it is piecewise linear. So on the interval 0, 1, so f is defined from 0, 3 to r is piecewise linear. Now let us compute Ax in this case. See, here when you compute Ax, you will have to compute it separately for values on the interval 0 to 1, then 1 to 2 and 2 to 3. Okay? So we do that. Start with X somewhere here. This is something which we have already computed. Therefore you see that on the interval, so you see that your Ax is going to be half square. So area of this. And that is true for X belonging to now you take up the case when X lies between 1 and 2. Suppose X is here. Then what is the area that you have to compute? You have to compute this area, whole area, which is actually the area of this triangle and of this rectangle. Therefore, this is equal to, what is the area of this? This is 1 by 2. The area of this triangle is 1 by 2. And the area of this rectangle is x minus 1 into 1. So this is equal to, now you know how to compute it. Now you take X to lie between 2 and 3. So choose an X somewhere here, and then you have to compute the area of this whole region. This is what we have to compute. So when you compute this, you see that it is a triangle here up to this, and then a square, and then a rectangle plus a triangle. That's how you calculate this. So if you compute this, see, you have half plus 1. Now compute this. This is going to be x minus 2 into 1 plus x minus 2 into 1 plus this is x minus 2 times this height. Now what is this function? This function is y equal to x minus 1. Okay? Therefore, it is, the height is 1 here, and this is x minus 1 minus 1, so this is equal to x minus 2. So it is x minus 2 half of x minus 2 whole square. Now if you compute this explicitly, then you see that it simplifies to. Okay, so what is Ax? Half of square for x belonging to This is equal to x minus half, and this is equal to half of for x belonging to. So let us draw the graph of this. Now you see it's a smooth function. It's not linear anymore on or piecewise linear. Or the f is piecewise linear, but at least on two intervals it is not. So whenever it is very constant, you will get the corresponding one. And you get here half x square. So this is 1, so this is half. So you see that this is equal to. Now at 2, what is the value? 2 is 2, it is 3 by 2. So this is 1, 3 by 2. Now this, here it is linear. And at 3, eventually it is going to be 3 minus 2 whole square, that is 2 square, that is 4, 4 plus 2 is 6, 3. And this is 2, I have drawn earlier. And then up to 3, it's again parabolic. So it is linear here, on these two it is parabolic. But it is differentiable everywhere. That is true. And one verifies that a derivative of x. It's quite easy to verify. Because if you differentiate this, you get x, get our definition for f, and the derivative of this is equal to 1, and the derivative of this is x minus 1. Therefore, we get the function ax as the antiderivative of the given function f. More generally, you compute this. Suppose you call for any x. Now you see you have to compute this for various values of x. X between 0 and 1, x between 1 and 2, x between 2 and 3. So compute. That means the options are both a and x belong to the interval 0 and 1. Now a belongs to, the second option is a belongs to 0, 1 and x belongs to 1 to 2. The third option is a and x are both in the interval 1 and 2. Now another option is a is in the first, that is 0 to 1, x is in the interval 2 to 3, and so on. So all sort of possibilities such that a is less than, and if you do that, you can verify this. I leave it you. Once again, you are left with this result. Now, a word of caution: the ax that we have to use. Suppose you are taking a is in the first interval, that is 0 to 1, and x is in the interval 2 to 3. Then you see that ax you should be using for the expression on the interval 2 to 3. Okay? A will be the expression that is there on the interval 0 to 1. So that is how you have to show this. So there are a lot of computations that you can do, put your hand on, and you get a good experience of working on it. And in all cases, you verify this. Okay. Once again, you see that A, in all of these cases, derivative is equal to x. In other words, AX for a fixed A is going to be another solution of this equation or an antiderivative corresponding to the function f. This is what we have to do. So that's the third example. Now I'll take a fourth example where again lot of computations will come which you have to do after. I am taking this for some reason which we would be needing in the later development of the theory. So far we have been taking fx to be continuous. Now we are going to break that law. So we take this over 1.